take a 3 by 3 vector and to teach you, I'm going to take more and more time. So maybe I can just take up a 2 by 2 vector, teach you, and I can translate the same idea into a 3 by 3 vector also. Okay, so it's something similar, so it should not be very difficult. So मैं शायद राइस और दाल की जगह बोलूंगा राइस दाल फ्राई बना लेना एग्जाम में, ठीक है, नॉट लाइक चिकन बिरयानी. That much difficult. Let's take this example. Okay, eigenvalue and eigenvectors, and I'll just show you the steps that we need to use. If you have already done it, you can again do it. The more you practice, it's always better. Let's just take up one example and at least explain it to you better. Okay. So when you actually take up the eigenvalue and the eigenvectors, you first need to start with the matrix. We do have a matrix, let's say A. Okay, and let's say if you have a matrix which is n by n, matrix is let's say 4 by 4, 5 by 4, whatever. Okay, we are going to have the eigenvalues as lambda 1, lambda 2, and 2, let's say lambda. Okay, so this is a 2 by 2 matrix. You can see it is 2 by 2. So that means we are going to have a 2 eigenvectors, right? That is the first thing that we are going to observe. And if there are certain properties that we need to know, so that whether we have calculated the correct eigenvectors or not, we can actually easily assess from this. Okay, and this is something which you might have studied. This is actually a trick that you should know actually for your exam purpose also. If you basically sum up all the eigenvectors, maybe is equal to 1 to n, okay, and take up these eigenvectors, okay, this will be actually equal to the trace of the matrix. So trace, if you just add the diagonal element, so you see the trace here, 3 minus 2 is 1, right? So that's the trace. So that is one property that probably we should remember, so that when we really calculate the eigenvectors, and during exam time, it's in a hurry that we are doing, sometimes we do make mistakes. You should always have this practice of checking it twice. And if you just multiply all the eigenvectors, okay, this should be equivalent to the determinant of A. We are only going to see that this property, we are going to use it. This property, we are going to use it. So determinant of A. Okay. So let's just do this particular sum. Okay. Maybe I can just show you the steps. Okay. Not in detail. Maybe I can just do it a bit fast. So first thing, when we actually put this property inside bracket, okay, this is just for clarification or something you should recall. First, we usually write down the characterization equation. Okay, that's the first step. Okay, there is a big difference between giving an exam which asks only objective question and writing an answer for a question which is asked by an institute to give you final marks. Okay, there you should be more detailed. Okay, because you have your seniors. Okay, who are in IITs now doing PhD. Okay, some of them has cleared their JRF test and all. Okay, so one of the students who has cleared JRF net, he's actually a very good student. Okay, but he cleared JRF net, but the way he used to write down his answers in exam, okay, it was actually like nothing, very short. Okay, it's as if a PowerPoint presentation point. But that way you cannot write it. I mean, exam you have to be a bit more detailed. That is very important. Okay, well, I should understand whether you understood the topic or not. That is very important. Okay? Because in future, if you become a teacher, eventually you have to understand that a detailed study is far more important than just giving the final answer and saying that you know this, you know that, you can try this, you can try that. Okay, every time you cannot do that. Okay, so that's also a training that is important. So characteristic equation we write down A minus lambda I, where I is the identity matrix. We need to multiply every time lambda with I, because we're subtracting, we need to subtract it in the matrix form. Okay, so is equal to 0. And eventually, if you just calculate it, okay, I think maybe we can just do it fast. Okay. Minus 1 or minus 2. Okay, maybe let's take this up. Yeah. Okay, and minus of lambda. Okay, then this is 1, 0, 2, 1. So we can just equate this to 0. Okay, and then we can just take this determinant directly now. 3 minus lambda, and this is 0, right? So it's minus 1, then this is 4, okay, and then this is minus 2 minus lambda. Actually is equal to 0, okay. And if you just do the calculations here, okay, I'm going to do it, I think you can do it easily. Should be lambda minus 2 and lambda plus 1 is equal to 0, okay. So just cross check that once, okay. And then to actually get the eigenvalues, okay, they are independent of each other. So I can just say that lambda is equal to 2, let me take this as one value, and lambda 1 is equal to, lambda 2, sorry, is equal to minus 1, right? So these are the two eigenvalues that we have, and this is the first step. When you get a question on eigenvalue and eigenvectors, sometimes the marks gets a bit divided. So I might give you a mark then based on this, okay? So if I have value calculated, then maybe I can just give you some mark. Okay. One second. Okay. So just calculate the eigenvalues now. Okay, sorry, eigenvalues calculate just like the eigenvectors. Okay, so here what I said was about checking. Okay, so this checking you might not include. Okay, but then if I ask you specifically, there will be some tricks or in exams online. Number 2 is equal to 2 minus 1, which is equal to 1. Okay, and then take the summation, it should be equal to trace of A. And what is trace of A? Trace of A means sum of the diagonal of the original matrix. So it is 3 minus 2 is again 3 minus 2 is equal to 1. So that means this is correct. Usually we do, because sometimes if you make mistake, we are sure that okay, the values are correct. Okay, that's very important. Then let's take the multiplication. Lambda 1 into lambda 2 is equal to 2 into minus 1. This property you can call once minus 2. Okay, and then if you take up the determinant of A, so determinant of A is 3 into minus 2 is minus 6, and this is plus 4, right? So this is minus 6 minus of 4, right? This is minus 6 plus 4 minus 2, right? So this is also correct. So if these things are okay, that means your eigenvalues are correct. Okay, I would suggest all of you to do it. Okay, and even if you don't show it in your exam, it's fine. You don't need to show it. It's for your satisfaction that you have done it correctly. That is very important. I am doing it slow because I want everyone to understand this. This is important. Okay, and then what we do is we actually calculate the eigenvectors. I've just taken up this example. Even if I give you three vector, three by three matrix, should be able to more or less do it, right? Okay. So eigenvectors, there are different ways of representing it. I can also represent it in this way. Okay, maybe this way. The matrix is equal to lambda. Basically, this notation is used a number of times in quantum mechanics. Okay, so in general, if I just write it down as, let's say, x this way, this will be a column matrix, like maybe x1, x2, just an example. Okay, but in general, if I just change this to a matrix, usually we follow this notation in quantum mechanics. We eventually going to use it x1 and x2. Let me just give you this introduction at the beginning. So this is something which you may note. This is a way of representing the matrix form. Okay, so this is better. Okay, so this is your eigenvector equation that we have, and when we actually want to write down, find out the eigenvector, we just simply say that when lambda is equal to, let's say, 2. Okay, so lambda is equal to 2, maybe we'll just show this step. If you have missed the last class or something, you don't remember, and then this is maybe I can just write it down as x1, x2. Okay, this is the cat notation. Okay, these notations are used in quantum mechanics regularly. You will also learn about it later if you have not already done it. X1, x2. This is 2, right? So if we just do it, okay, maybe we can write down the equation here. So this multiplied by this. So this is 3x1 what minus x2, if I like to tell me, is equal to 2x1, one equation, and the second equation is 4x1 minus 2x2 is equal to 2x, something like this. Okay, and if you just check here, it is 3x1 plus 2x1, so this is x1 minus x2 is equal to 0, right? In the second equation, this is 2 minus 2 will go on this side, so it will be minus 4x2. So 4x1 minus 4x2 is equal to 0, so this is again x1 minus x2 is equal to 0. Now these eigenvectors can have infinite values, okay? And this is actually nothing but which is unique. The lambda values are unique. Okay? That's why you actually get the same equation. So that's important. Okay? So here we can actually assume this. Okay, we can basically just take up the value of x1 and x2. Okay, so in general we can conclude that x1 is equal to x2. So I'm just giving you a step-by-step way to do it, and we know this is x1 is equal to x2. So what we can do is we can just assume. So what we do is in general what we say is let x1 is equal to 1, then x2 would also be equal to, right? We can assume one value and then we see. So eigenvector, you can understand this here. The eigenvector actually gives you a relation between x1 and x2. Okay? So eigenvector will give you that relation. So if x1 is equal to 2 times of x2, we know that what is the relation between x1 and x2. There can be infinite number of values of the chosen ones. Okay, you can take up the value. I said x1 is equal to, I can say x1 is equal to 2, 3, and 4. So there can be infinite number of combination, but the relation between x1 and x2 will remain the same. Okay, so in general what we do is, as we also discussed the other day, we can always write it down in the normalized form. Okay, if we just write it down in the normalized form, what I can do is I can write down 1 divided by root over of 1 square plus 1 square. Okay, so this will be root over of 1 square plus 1 square. Okay, and then this is the values that we have. So it is basically a column matrix. Column matrix, row matrix, we should remember. Okay, that's important. So this particular thing, maybe I can just write down the complete one. 1 divided by root 2 and x1 and x2. Okay, and this will actually give you the eigenvector. Okay, so this is something that is the eigenvector. So when you do it in exam, you should be very clear for what values you are calculating, and your final answer should also be very clear. Okay, so I will try to do it very clearly, because I say it and then I don't teach you that clearly, then again it is contradictory, right? So I'm just going to do it. Let's just complete this. Okay, and let's say for what was our other value, lambda is equal to -1. For lambda is equal to -1, we again do our calculations, right? So it is 3 minus 1, 4 minus 2. If you understand things, even if you write it in detail, probably it's not going to take that much of time, but then basically do it. Okay, is equal to -1, and then this is x1, and then this is x2. We'll try to solve it in a similar way. If you do it, it will be 4x1 minus 2 is equal to 0. You can do it verbally also. Everything you don't need to put it there. The second one will also be 4x1 minus x2 is equal to 0. You can check it once. That should happen. Okay. So in general, we can say that x2 is equal to 4 times x1. Okay. So this is the relation that we have. So what you can say is, therefore, if x1 is equal to 1, x2 would be equal to 4. So you see, you get a relation between x1 and x2. Okay. So therefore, again, if you just take out the normalized value, just write it down as 1 divided by root over of 17, and this is 1, and this is 4. Okay. 2 by 2 matrix. Take 2 matrix, there will be 3 rows, right? Sorry, 3 columns. Yeah, 3 rows. Okay, 1 column. Yeah. So that's so now. Therefore, what we can say is equal to 3 minus 1, 4 minus 2. Okay. The corresponding answer that will be 1 divided by 2, 1, okay, and number 2 is equal to minus 1 divided by a power 71. Okay. So this is very detailed. Okay. Of course, you can just sometimes you can skip that, like this step you don't need. Okay. Then here more or less you need everything. Go to the previous page. To make this. We should actually practice. So you should practice it this way. It will be much more easy. So what I suggest all of you to create, okay, on the road and practice as much as possible on a 3 by 3 vector and so on, okay, because mathematical physics, whether it be asking you for similar, I mean, same question definitely solve. Okay, have a look into a theorem. Okay, let's just look into a
So your voice is breaking.
voice is breaking. Okay. Okay, what you can do is you can just have a look at the screen right now. At this moment, we really don't need to, uh, even if there is a bit of lack of verbal communication, still you can understand. Okay, let's just write down this theorem first, and then I'll explain. So if there are lambda 1, lambda 2, of matrix A, then the on eigen vectors will linearly independent to linearly independent to each other. So if we have lambda 1, lambda 2 up to lambda n, these are all nothing but the eigenvalues, okay, if the eigenvalue of the matrix, okay, of matrix A, then the corresponding eigenvectors will be actually linearly independent to each other. This is what we want to do, okay. So in general, what we can do is we can write down these equations, something like this. A, maybe I will take the um, put my mobile and do not disturb. So is equal to lambda 1 phi 1 A phi 2 equal to lambda 2 phi 2. Okay. And then we have put A phi n is equal to lambda n phi n. Okay, so what happens here is this, okay. Mm, see this, you have got this form, I think yesterday we have already said. This is the matrix that we have, okay. These are the eigenvalues, and these are your eigenvectors. Okay? These are your eigenvectors. So this is something which we have, okay, and we have actually, let's say, calculated lambda 1, lambda 2 up to lambda n, all these are distinct. We have to show, okay, that this phi 1, phi 2 and so on, okay, they are all independent of each other, okay, linearly independent of each other, okay. So this is something which we need to show, okay. So I will just try to prove this technique, which may be a bit lengthy. Okay, this is the way that we need to prove this. Okay, so what we will do is we will say that, let's say, phi 1, phi 2, okay, and then phi n or eigenvectors. Okay, so what we can say is that if they are linearly independent of each other, right, we can simply say that we can actually write it down as we right now don't know they are linearly independent or not, but if we use the vectors here, okay, we can simply say c1 plus c2 phi 2, and then I will take up c3 and then phi n, sorry, not c3, c phi n is equal to 0. Let's say this is our first equation. Okay, we have this equation. Okay, now here what you have to see is you have to note this. Note, you don't really write it down when you prove it. You have to note this, that if phi 1 up to phi n are linearly independent, okay, then we have to show that C1 is equal to C2 is equal to Cn is equal to 0. C1, C2 and Cn, all these should be 0. Then only we can say that phi 1, phi n are linearly independent. Okay, this is something which you see, but this is something which we have to prove. Actually, we have to prove this. And if we can prove this, we can say that these eigenvectors are linearly independent of each other. Okay, so what for this, what we do is we actually do something which is not that complicated to understand. What we do is operate equation 1. We actually will operate equation 1 on both sides. Okay, on both sides by a minus lambda I. Let's just try to operate this on both sides. Okay, so how do we usually use the operations here in general? I'll tell you. This is something which you need to done in quantum mechanics also, when you use the bracket notations. Okay, so you have got this C1, and then this is phi 1 plus C2, and then I will take up phi 2. It is slightly long, okay, the derivation. Cn phi n is equal to 0. On this side, if you operate, everything is going to be 0, right? Okay. Let's operate this now. A operates on C1 phi 1, right? So if A operates on that, A phi 1 is lambda 1 phi 1, okay? A phi 1 can be lambda 1 phi 1. C1 is a constant. You take out C1 here, okay? And A operates on phi 1. So A phi 1 is equal to lambda 1 phi 1, okay? So I can take up this one as lambda, okay? And then, sorry, I have to write this down as lambda 1. Sorry, not lambda, it's lambda 1, okay? Lambda 1. So lambda 1. So this is lambda 1 because A operates on phi 1, C1 is here, I've kept it here. Minus, I can take this lambda 1 bracket. 1 into phi 1 can be written as lambda 1 phi 1 because I is an identity matrix. So I simply say lambda 1 I into phi 1 is nothing but lambda 1 into phi 1. So I have got phi 1 which is common, both the cases. I can just take out this. So look into this operation and just be a bit clear. This is a bit of used in quantum mechanics, but it's a part of mathematical physics because this is an operation. So I'll just explain this once again. A operating on phi 1 will give you lambda 1 phi 1. So A operating on phi 1 will give you lambda 1 phi 1. And then lambda 1 I operating on phi 1. I is an identity matrix, so it will remain as phi 1. So it is phi 1. Lambda 1 I've just taken it here. Okay, so this is the first. Similarly, I can do with the second term. In the second term, C will remain constant. Okay, and then A operates on phi 2. So A operates on phi 2, you'll have lambda 2 phi 2. So this time I'll have lambda 2 minus, this is lambda 1, this will remain as lambda 1 only. I operates on phi 2 will remain as phi 2. So this will be this, and then I'll take phi 2. This is how these operations are carried out. Okay, if we just read a bit more or concentrate a bit more, it should be easy. So similarly, if I did the last term, it's something which looks similar. It's C2, so this will become Cn. This is phi 2, so in the last term it will become, sorry, not phi, okay. Lambda n will become lambda n minus lambda 1, right? So this will remain as lambda 1 because you know this is lambda 1, so it will remain like this. Close it. The final term is phi n. So I think we can take a hint from this because you know here this term will become 0. So we're getting rid of this particular term. So if this becomes 0, we are just left with C2, lambda 2 minus lambda 1, phi 2, and then Cn and so on. Okay, so this is our second term. Okay. Now once we have the second term, what we do is we operate on the second term by A minus lambda 2. Okay, let's do this step now. And now we can actually do it faster because you understand this. Operate by A minus lambda 2 into I. Okay, so if we do that, now we have got A minus, actually I can write it down again so that I or you get confused, lambda 2 into I now. Okay, this is here, and then it will be C2, C1 is now, okay, C2 lambda 2 minus lambda 1, and then this is phi 2, and I will write down the next term. Let me write down the final term. Cn lambda n minus lambda 1, and then this is phi n is equal to 0. Okay, so that's it. So this is there. Okay, and what I will do now is just operate this again. Okay, so for this I think you can understand this. I will take up C2 as a constant, and here you know I said that in this particular case we have got this lambda 1, whatever is the coefficient of phi 2 actually can be considered to be constant. So I can just take this out, lambda 2 minus lambda 1. Okay, so this is the C2 and this is lambda 2 minus lambda 1. I've just taken it here. Okay, and then I will do the operation. I will operate with A on phi 2. To operate with A on phi 2, I'll be left with lambda 2 phi 2. And then this is lambda 2 operating on A on phi 2. It will be nothing but it will be left as lambda 2, and this is I. Try to understand this. This entire part this on 2 and 2, operate this on phi 2 and lambda 2 phi 2. So this similar vanish. Then I can actually write down the next one. This is going to be lambda 3 minus lambda 2, right? So I'll keep on writing this, and I will finally get this to be lambda. Let me just write down this lambda n minus lambda 1. Okay, and then this is nothing but phi n will be equal to 0. Okay. So what we can do is we can actually do n number of operations like that. Okay. So sorry, I miss out something here. Yeah, C2 lambda 2 minus lambda 1 and lambda 2 minus lambda 2. This is fine. Sorry, there will be a lambda 2 minus lambda 1. Okay, lambda 2 minus lambda 1 is there. Okay. Okay, so if we just do n operations, okay, so this is something which is going to continue. Now this will become 0 and the C3 term will be there, and again we will operate with A minus lambda 3 into I and so on. Okay, so if you just operate on this, let me just move to the next page. Okay, so what we are going to do is we are going to have n minus 1 operations. Okay, so if we do that, finally what we're going to have is we are going to have the nth term, okay, and then we are going to have, let's say, lambda n minus lambda 1, okay, and then lambda n minus lambda 2, okay, and then we are going to have lambda n minus lambda n minus 1, right? If you remember, n minus 1 operations, okay, it's not n operations, okay. If we do that, okay, sorry, so this one would be, there will be lambda n minus lambda 2 will also be there, right? So this is the second operation, and then if you just keep doing it up to n minus 1 times, you're going to get this term, okay, and then what we have is finally phi n here is equal to 0. Now you know all the lambdas are distinct here, okay, the lambdas are distinct. That means it's not that two lambdas will actually have the same value, okay. So if that is the case, how can I have 0 here? The only possibility of having a 0 here is if this Cn is 0. Lambda n and lambda 1 are not equal, lambda 2 and lambda n are not equal, lambda n and lambda n minus 1 are not equal, all of them are distinct, okay, and this is the eigenvector, this will be 0. So the only possibility is that Cn is 0. If this is the case, if lambdas are distinct, already know it, okay, hence Cn is equal to 0. So in this way, we have proved that Cn is actually 0. Okay, so let me just put this here. Okay, and then we can write down therefore C1 phi 1 plus C2 phi 2. If we are actually proving it for the nth term, that should be true for the first term, second, and so on. Okay, Cn minus 1 phi of n minus 1 is equal to 0. Now you understand what I did here, right? We ignored the Cn because we said that Cn is 0, so the Cn term will be 0. The term before that, we have just put it here, okay? Now what we do? We similarly repeat the operation, okay? Now what we do? Now we start again doing the same thing, and we eventually see that even Cn minus 1 is going to be 0. And then Cn minus 2 is going to be 0. Eventually, everything should be 0. So what we do is, if we just similarly repeat similarly repeated, I'll just read out the sentences here that you may have to write, okay. Repeated operations can show operations can show, okay, that C1 is equal to C2 is equal to C3 is equal to, okay, Cn is equal to 0, okay. So it means that therefore phi I, let me write it down, any generally generic vectors, okay, these are linearly independent vectors, and these are proved. So that's the proof of how to show actually the vectors are linearly independent. So you know we have done an iteration method where we actually usually follow the steps, okay, multiply each other, okay, and then the next step and so on. Prove one Cn is 0, obviously the remaining term will also remain as 0, okay. So this is one more thing that I'd like to tell. This is the theorem. So for your exam, maybe I will just ask you this, okay. I'll give you the theorem and then say just prove it, okay. So if there are distinct eigenvalues of a matrix A, then the corresponding eigenvectors will be linearly independent to each other. Proof, okay. That's it. So you can do it in that way, okay. One more thing that we haven't done it yet is normal metrics. Okay, this is also something which you might have done, and this is something very trivial. Okay, you already know, I think, about it. Maybe sometimes we don't use the term much. Normal metrics. Does anyone remember what is a normal matrix? If am I still audible? I'm audible, right? You know, even voice breaks. Still, I'm writing everything on the board, so I think it should be more or less clear. Am I audible? Is my voice okay?
Yes, sir.
Yes, sir. Yes, sir.
Oh, breaking, yeah, I know. But I think that's the advantage of having a mathematical physics class. If you write it, then everything might not be much difficult to understand. So if you can just write down a dagger, transpose conjugate, okay, A is equal to a dagger, okay. Already we talked about Hermitian matrix, okay. We also can say that if this is the case, okay, A is basically nothing but a normal matrix. So sometimes there are simple questions, okay, where it is asked that prove that the matrix is normal, okay. So it's just a term, and you actually already know how to do these things, okay. So I will just take one example here. It's A is equal to 2 minus 1, 1, 2, okay. And the question is A a normal matrix? It is proof if A is a normal matrix. Okay, so can I just take a 2 minutes break and do it fast? You can do it fast, okay, and tell me the answer. Okay, 0, 5, right. Okay, so all of you will do it. Okay, if you remember your matrix multiplication correct, you should not be having an issue. You should be getting 5, 0, 0, 5. Okay, that's correct. So when you get both of them equal, you know that it is actually a normal matrix. So this is one thing, okay, and this is something which is very trivial. I just wanted to introduce this, or at least introduce this for this class, okay, so that I know that all of us are on the same page about it. Okay. Next is whether there is one more thing that usually comes, whether eigenvectors are orthogonal. Okay, eigenvectors. So normally when I say that I'll take classical mechanics, or someone takes quantum mechanics, atomic and molecular physics, sometimes your study is a bit limited because you follow the book and just do it. Mathematical physics, just like maths, more you practice, the better you are. Okay. So let me just take one example here. Okay, let me just take one example. Let me say I will take a vector, a matrix 2, 1, 1, 2. Okay, and then I will calculate the eigenvalues in a similar way, which we have done. You can always do it, okay, on your own, practice it. I'll probably just write down. So I think I got it as 3 and 2 is 1. Okay. So we have got the eigenvalues, sorry, and I can actually calculate the eigenvectors from there. Okay. And eigenvectors for lambda 1 is equal to 3. Okay. We can just use this notation. Okay, you can just write down a vector notation and write it. But then I think it's preferred this is accepted x1, x2, and then t1, 1. I can also normalize it, no problem. But I'm not doing it right now. Okay, and I'll tell you because I want to just check the orthogonality. That's it. Okay, and lambda 2, if we do it, we get just 1. And then let me just represent it with another vector, let's say y. And let me say this is again, let's say y1, y2, y1, y2. I can also write down x1, x2, doesn't matter because I've already defined it for lambda 2 is equal to 1. Okay, so there maybe this is n minus 1. So just calculate this, okay, to get this hopefully, okay. And then if they are orthogonal or not, I'll just show this because I think this is something which I've told you in the last problem. When you write it down in this form, you're taking the blah version, okay, written in cat format, okay. You just take this up. This is 1, 1. So this was actually a column matrix. This will actually get converted into a row matrix. Okay, that's it. So therefore, if we just take up the bracket properly, x y. Okay, let's take up this as 1 1. This row matrix will be multiplied with the column matrix of y. It is 1 minus 1. So in 1 into 1 is 1 plus 1 into 1 is minus 1. So 1 plus minus 2 is 0. If that comes out to 0, it's basically an orthogonal matrix. And then the matrix has to be normal in that sense. Okay, it has to be normal, and then we can say it is actually an orthogonal matrix. So maybe a question maybe that shows that the matrix is orthogonal. Okay, and then show matrix is normal. Okay, and they are orthogonal. Okay, so both these questions might be together, and it's just it's a matrix which is we are having it in 2 by 2 format. Okay, so we can actually show that it's an orthogonal matrix or not. So similar problems will be asked in exam also if we just practice it once. Okay. Okay, and then actually the next topic is a bit long. It will take around 15-20 minutes. So I'll just do one problem on diagonalization of matrix. Okay.